will go for the design of the design for the dynamic loads, and in that we will start mostly focusing on the stress concentration today. So to start with, during the manufacturing, there are a lot of inaccuracies that would prompt during the process of manufacturing. So due to inaccuracies inherent in all manufacturing processes, no component can be manufactured to exactly given dimensions. Hence, we will have certain kind of deviations from the given size. So, but we know that usually manufacturing to a higher accuracies requires more labor and results in higher cost. So we have to have certain kind of tolerances for that. So for that, first we need to write functional requirements of a designed product do not demand exact dimensions. So further, they are satisfied even if the dimension of the product deviate to certain extent from the nominal dimensions required by the design. So now we need to know that to what extent these, the question is to what extent these deviation can be tolerated. So, and that should be specified by, and this has to be answered by the designer like us. So since you don't need exact, you can live up to certain deviation for a given design, which would be specified by the designer. We should know how these tolerances can be, or this deviation can be quantified. Okay, so and we need to know what is the maximum minimum limit of these things. So component are manufactured such that their dimensions lie between maximum and minimum limits. So when we talk about tolerance, tolerance is defined as the permissible variation in the dimensions of the component. Tolerance. And but in order to quantify it and so that we can mention it in a proper manner, we will try to study some definitions looking at the deviations that can be observed between a kind of assembly between a hole and a shaft. Okay, so let me just pull up a picture. Now, if you look at it, this is the kind of a hole. There is certain deviation in manufacturing there, and there is also shaft. There is certain deviation in that. So if you look at it here, this is, as you are seeing here, this is the hole, and this is the shaft. There are certain things you need to kind of see here. This is the kind of maximum diameter. You can see here. This is the maximum diameter of the hole, right? From here to here. Similarly, and the minimum diameter one can tolerate is, let's say, is here to here. This is the minimum diameter of the hole. Similarly, if you come to the shaft, on the shaft line, so this is the minimum diameter. This is the minimum diameter of the shaft, and this is the maximum diameter of the shaft. And then there is something called as a zero line, from which, or the line of zero deviation is the zero line. And this is the tolerance that is seen in the kind of a shaft. And similarly, this is the tolerance that can be observed in the hole. And then you need to also mention from the zero line, you will see what is the lower deviation, and this is the upper deviation. This is the upper deviation for the maximum diameter, and the lower deviation is for the lower diameter. Similarly, you can also see here from the zero line. This is the zero line. This is the lower dimension for the lower limit and or the minimum diameter, and the upper thing is for the upper deviation is for the maximum diameter for the hole. And based on this nomenclature, what we'll do is we'll define certain definitions, so that based on these definitions we'll come up for a quantification as per the international standards. So the first definition, nations, first one, the basic dimension is also called as normal or basic size. Next, the upper deviation is the deviation of the basic size from upper limit. Similarly, the lower deviation is the deviation basic size from lower limit. So the lower limit would be the minimum diameter, upper limit would be the maximum diameter in this case. The tolerance is again redefined, is defined as the difference between the upper and lower limits. So in order to mention these tolerances, specifying the tolerances, there are two methods. In the first method, which is also called as Uni Unilateral Method, in this, one of the deviations is 0. That is either upper deviation or lower deviation is 0, and from there it is mentioned. Whereas in the bilateral, none of them deviations are 0. So you don't need both the deviations has to be 0. You can still have both the deviations to be non-zero. So if one of the deviation is 0, you can go with the kind of unilateral specifications. Now, when two parts are assembled, while two assembled, the relationship resulting from the difference between their sizes before is called a fit. And there are three types of fit. First one is clearance fit. Second one is transition fit, and the last one is interference fit. Now, in the clearance fit, always provides a positive clearance between the hole and the shaft over entire range of tolerances, while interference fit always provides a negative, or we can say it as a positive interference, which is as good as saying as a negative clearance, because clearance and interference are kind of opposite to each other between the hole and the shaft over entire range of tolerances, while the third one, which is transition, may have either a clearance or interference fit, depending upon the actual values of the individual tolerances of the mating component. So further, when you want to kind of describe the tolerance, so in the description of tolerance, one has to follow the following things. Has to know, the first thing is it consists of two parts. The first one is fundamental deviation, and the second one is the magnitude of tolerance. So if you want to kind of understand this in a pictorial manner, one can clearly show that if you have a zero line, as I showed above, this is the zero line. Zero line is the line for the basic dimensions, and then this is the magnitude of tolerance, which will be varying from this place to this place, but this is the offset of this magnitude of the tolerance from the zero thing is called fundamental deviation. So this is how, so from the zero line, what is the fundamental deviation and what is the magnitude from the deviation, fundamental deviation, it is allowed. So if you mention these two, then you can completely describe the tolerance. So further, when you are mentioning this tolerance, you need to know that you need to mention the zero line, and zero line comes with the basic size. So tolerance is preceded by basic size. Further, fundamental deviation is denoted by alpha bet, and such that uppercase letters, uppercase for the wholes and lowercase for the shafts. So for example, I will show it here. So if you look at here, this is the fundamental, let's say this is for the holes. You can see that all these letters like A, B, C, C, D, D, E, E, F, 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 G, G, H, and so on like that. And this is your zero line. You can see this is the negative side of the deviation, and this is positive side of the deviation. And you can clearly see that this capital H has a zero deviation from the zero line. Similarly, look for this, which is for the shafts. This is for the shafts. For the shafts, the A starts from the negative and it goes further to the positive side as it goes further. So, and if you look at it, H has the zero deviation from the as the zero fundamental deviation from the basic size. Now, similarly, this is for the fundamental deviation. The fundamental deviation is mentioned for the holes in the capital letters by this, and for the shaft using this one. The next is magnitude of tolerance is denoted by a number called the grade. And each grade is assumed to have some accuracy, and there are 18 grades of tolerances as per the international standards. So as per the international standards, this grade values or the magnitudes of the grades are given by okay, let me just recopy it. So if you look at here, this is kind of different tolerance grades, and you can see that it starts with 0, 1, 0, and it goes up to 16. So if I count all this 16, plus 1 0 and plus 0 1, there would be 18 such kind of things. And if you can see that for the different diameters which are mentioned in mm, the different tolerance grades has different magnitudes. So up to and including 3 mm as a diameter, a kind of, let's say, a 3 tolerance grade has a 2 micrometer, which is mentioned here, are kind of tolerances has to be, is the magnitude of the tolerances. So like that for different, let's say if a diameter is 40, then we need to look into this one. A grade 7 says that this has up to 25 micron meters as the magnitude of the tolerance. So using this table and using this alphabet, one has to determine the fundamental deviation as well as the magnitude of the tolerance. So these tables are used. Now we will have a look at certain examples, so that it makes clear what we are talking about. The first one, if I say 45 capital G 7 by 45, or people can also mention it as 45 G7 dash G7 dash 45 mm or mm means, in this case, in both the cases, basic size is 45 mm and fundamental deviation G7, right? And is fundamental deviation is G, and sorry, I think I have just messed it up a little bit. It is mentioned as G by 7. This is so let's say it is 45 G7. If you mention it in this manner, then we know that basic size is 45 mm, fundamental deviation is G, and magnitude of deviation is grade 7. So 45 mm is the basic size. It is not a problem. For a fundamental deviation G, one can look into the tables and one can say here it is, the values are not mentioned, but we know the capital G mentions that this is for the whole. So this is for the whole and the value is plus 9 microns, and grade 7 says that, so for 45 mm this you have to see here, and grade 7 says that this is 25. So if you look at it, the grade 7 and under 45 it is 25 microns, so is 25 micrometers. So that means we can calculate our limits as 45 plus 9 that is equals to 45.009 mm to 45 plus 9,000 plus 25 by 1000 that is equals to 45.034 mm. So the limits of it is 45.009 to 45.034 mm is the tolerance we are allowing for the hole of a diameter 45 mm. This is the lower dimension, lower limit, and the other one is the upper limit. Similarly, and another example of 45 f8 means basic size 45 mm. This fundamental deviation is f, and grade or magnitude of tolerance is of grade 8. This means it is 45 mm. F comes with a fundamental deviation of minus 25 micron meters. I haven't provided the table. This should reflect it. This F minus 25. I will provide you table at a later point of time, and the magnitude grade 8 says that 8 and over 30 to 50, because our 45 lies here, it is around 39 micrometers. So together we know that in this case the lower limit is 45 minus 25 divided by 1000. It is 45.0 so 44.975 mm, and 45 minus 25 by 1000, and the magnitude starts at that point and goes towards the opposite direction. So it is, in this case, it is 44.936 mm. So our limits is from 44.936 to 44.975 mm is our limits. Now for the hole and shaft assembly is denoted by 45 is the basic thing, G7/F8 or 45 G7-F8 is the standard notation. So this tells for the hole, and this is for the shaft. This is for the hole, and this is for the shaft, and this is our basic dimension. So further, Now, when we are mentioning the tolerances, there are again there are two systems for specifying tolerances to the shaft and the hole when you have both into the picture. The first thing is hole system or hole basis system is the first one, and the second one is shaft basis system. In the hole basis system, lower limit of the hole coincides now in shaft basis system, upper limit of the hole, of the shaft coincides with the zero line. However, mostly hole basis system is widely used because holes are machined by standard drills or reamers having fixed dimensions. While shafts can be turned or ground to any dimensions. So because of this reason, mostly hole basis system is used. Now let us have a kind of a quick view of different types of fits before we kind of proceed further. So first one is a clearance fit. In the clearance fit, we know that hole has to be greater than shaft dia. That means minimum clearance in this case is equals to minimum size of hole minus maximum size of shaft. The shaft has to be bigger and the hole has to be smaller. Then only the clearance between them has to be minimum. Now, when you have maximum, you want to have maximum clearance computation, then it has to be maximum size of the hole minus minimum size of the shaft. That will give you maximum and minimum clearances one can achieve for a clearance fit. Similarly, for an interference fit, in this interference fit, we know that hole dia is less than shaft dia. So the maximum same as the previous case, but this is interference, so minimum of hole minus maximum size of shaft, and similarly vice versa, minimum interference is equals to max size of hole minus minimum size of shaft. Further, in the third case, for a transition fit, hole diameter close to shaft dia, or it can be clearance fit or interference fit, depending on actual value of the tolerance. And the applications of this is different types of fits are so depending upon the size of fit, and let's say if it is a string fit has whatever might be the basic dimensions. It is like H8 by U8, which is you often see in the applications like wheel sets, tires, bronze cones, or worm wheels, etc. For example, if you look at a transition force fit, which is H7M6, can be seen in parts of machine tools that must be changed without damage, like belt pulleys, coupling fits, inner ring of ball bearings, and etc. Whereas if you come to the clearance fit, let's say if you are looking for normal running fit, which is H7 by F7, which is generally observed in applied in sleeve bearings with high revolutions, or bearings with machine tools, spindles, and other things. This table gives you a full list of the different types of fits that are kind of named fits and their corresponding symbol, and their examples are also given in here, which you can look into it. With this, we will end today's class. I wanted to take the next topic, which is designed for the kind of dynamic loads, starting from the stress concentration factor. Maybe because of the time, if I start, it will take a little bit longer than usual. So what I will do, but before, we will just have a look at different types of it in terms of kind of pictorial form. What is different types of widths with respect to the zero line. So just bear with me for another couple of minutes. So if you look at here, this one is the clearance fit. You can see that in the clearance fit, the shaft and the hole has a lot of positive clearance. This is the positive clearance. This is the positive clearance, which you can see, and this can vary from positive number to as close as 0 is the kind of clearance fit. Now, when it comes down to interference fit, this is your 0 line, and you can see that your hole is here and the shaft is on the higher side. So it can go from, it has negative clearance, or you can say as kind of a positive interference. So the positive interference can have as high as this to as low as this one. This is the interference fit, whereas the different clearance fit can vary from the transition fit can vary from the different things depending upon the actual position of the hole in the shaft, which is the it can change from one place to other place depending upon the actual tolerances involved. So this is kind of the things that completes today's topic on tolerances and clearances. So if you have any questions, please let me know.